Let us look at some special case of TSP. Okay, it is called metric TSP. What is metric TSP? Which is a more natural occurring TSP, because if you really look at in a map, then the distances, or at least in a road, the distances satisfy what is called the triangle inequality. Suppose that the points are on the plane, then you have, what is special about it? The distances satisfy triangle inequality. What is it? So, whenever you have 3 points I, j, k, the distance between I, j is less than or equal to distance between I, k plus distance between k, j. That it is always shorter to go direct than going through any other vertex. That is how, I mean, it is not generally true, but my distances satisfy this condition. I am going to look at that special class of TSPs, and then I am going to look at approximation algorithms for them. Okay. First thing I need to ensure is that special class of TSPs are NP hard first. They are actually polynomial time solvable, then why do I even care about approximation algorithm? Are they NP hard? Okay. So, that means, can you come up with distances that actually satisfy triangle inequality, and still you can reduce from some known NP hard problem. Okay. Actually, the distances we came up with satisfy triangle inequality. Remember, what was the reduction from Hamiltonian cycle to in that reduction, the distances were basically 1 or 2, right. If there was an edge in the graph, we gave a distance of 1, if there is no edge, we gave a distance of 2, and we argued that it is if and only if, so that is a polynomial time reduction and so on. So, suppose the distances are all 1 and 2, I claim that they satisfy triangle inequality. Let us see why. Right, in this reduction. So, if you pick I, j, k 3 points, d I j is at most 2, right, because the distances are 1 and 2, whereas d I k plus d k j is at least 2, because each one, I mean, there is only 1 or 2, and so d I k plus d k j must be greater than or equal to d I j, right. This 2 implies what I want to show, right. So, the TSP reduction I had from Hamiltonian cycle, the distances actually already satisfy triangle inequality. So, this special version is also NP hard. Now, in the rest of the lecture, I am going to give a good approximation algorithm for this special instance. Having ruled out good approximation algorithms for the general instance, I will show good approximation algorithm for this special instance, and it is going to use many things you learnt in the course in the first week. Okay. So, 2 approximation algorithm for metric TSP. So, 2 approximation means that the tour I will produce in this algorithm, whose total cost would be at most twice the optimum. Okay. Step 1. Remember, you have a complete graph with weights on the edges. Find the minimum spanning tree in the graph. You can do it in polynomial time, we have seen Prim's algorithm, Kruskal's algorithm, so many algorithms, right. Our goal is to find the Hamiltonian cycle, but what did I end up, what in the first step I have some tree like this. Step 2, double every edge of T. Okay. So, what do I mean? So, I just do this. So, your graph has a lot of other edges and lot of other vertices. Do they have other vertices? No. Why not? Because it is a spanning tree. What is spanning tree means? It contains all the vertices, but there are a lot of other edges. Your graph looks like this with lots of other edges. So, I found a minimum spanning tree and doubled every edge. So, what do we know about this graph? Every vertex has even degree. This graph, every vertex has even degree. So, you can find what tour? You can find an Eulerian tour, right? Polynomial time, we have seen linear time. So, all things which you have learnt, find an Eulerian tour here. All of this looks like a heuristic, right? I want to find a Hamiltonian cycle in this complete graph, minimum weight. Minimum spanning tree looks like something to start with, and I am going to do various things. Finally, I will produce a Hamiltonian cycle, but the important thing is I will argue about the quality of the solution. That is what makes this the complete thing. Okay. Otherwise, you can actually come up with some heuristic and produce some tour, but I will argue that it is not far from optimum. Find an oil. Oops. So, let us call this T prime, find an Euler tour of T prime. You can do all of this linear time, this is some n log n time, m log n kind of thing, right. So, there are 9 vertices here. So, the Euler tour, can somebody give me an Euler tour? So, I start from 1, go to 2, come back to 1, go to 3, 4, come back to 3, okay, I have to double this and then maybe 5, 6, 5, 3, 8, 7, 8, 9, 8, okay, 8, 3, 1, yeah. And remember, these each edge has a weight associated with it, right, the original graph weight. So, let us see, let us call this some C. What is the cost or the distance of C? The total distance of this Euler tour? 2 times the cost of minimum spanning tree, because what did I do? I just doubled every edge and visited every edge exactly once. Okay, good. Now, I am going to get a Hamiltonian cycle out of this Euler tour. Okay. Remember, the graph is a complete graph. Okay. Every edge is there. So, what is my Euler tour? Hamiltonian cycle. I call it H by short circuiting. I will explain what that means. So, I am going to traverse this Euler tour, except I am not going to repeat vertices now, because a Hamiltonian cycle cannot repeat vertices, right. I will just follow the same sequence. So, my Hamiltonian cycle will be, I will start from 1, go to 2, and then instead of going to 1 and 3, I will directly go to 3, and then 4, and then I will skip 3 because that is already visited, I will go to 5. 6, and then I am going to skip 5, skip 3 and directly go to 8, 7, 9, 1. Okay. So, what did I do? So, I started with 1, I went to 2 and then directly went to 3. Remember, this edge is there in my graph. Graph is a complete graph. And then from 3 I went to 4, then I went to 5, then I went to 6 and went to 8, 7, 9 and went to 1. and I am going to output this as my Hamiltonian cycle. Okay. Obtain the Hamiltonian cycle, output H. What is the cost of H? Yeah, first of all, cost of H is less than or equal to the total distance of C. Is that clear? Right? C is the cost of the entire this spanning tree, right? Every edge is twice visited and all that. The cost of the Hamiltonian cycle I have output is at most cost of this Eulerian tour. Why? Triangle inequality. This is exactly where I am using triangle inequality, right. So, what did I do? From 1 I went to 2, and then instead of going through 1 to 3 I directly went to 3, and triangle inequality tells me that that distance is shorter than 2 1 plus 1 3. So, if you keep following that, the final Hamiltonian cycle I have produced is at most the total distance traversed by this Eulerian tour, which I already argued is exactly equal to cost of the minimum spanning tree. Now, we will I have to give you a lower bound, right. Now, here is a small claim. The optimum TSP tour cost is greater than or equal to cost of the minimum spanning tree, in fact strictly greater than. So, to show this, what do I have to do? I will give you a spanning tree whose cost is less than this, right. If I give you a spanning tree whose cost is less than this opt TSP cost, I know that the minimum spanning tree may be even less. I will just produce you one spanning tree whose cost is less than opt TSP cost, and I know that the minimum spanning tree cost may be even less than that. So, what is that spanning tree? Take your optimum TSP tour, remove one edge. What do you get? You get a path. That path is a tree, it is a spanning tree. So, its cost is less than optimum TSP cost. So, the minimum spanning tree cost will be even less than that, right. So, proof, take optimum TSP tour. How do I take TSP tour? I do not even know how to find it, but that is just for the proof. I do not have, it is not an algorithm claim, right. Take your optimum TSP tour, remove one edge, we get a spanning tree with cost less than the cost of optimum TSP. Okay, so now that is it. So, minimum spanning tree cost will be even less than that. So, now plug this into here. What have I shown? Right, this the cost of t is less than opt of TS. So, what have I finally shown? The solution I have produced you the Hamiltonian cycle by this minimum spanning tree, doubling every edge, Eulerian cycle, short circuiting, that cost is at most 2 times the optimum TSP cost. So, the solution I have produced is at most twice the optimum. Okay. So, what we are trying to do, so in the case of vertex cover, we related it to maximum matching, which is polynomial time computable. We connected the cost. In the case of TSP, we connected it to the minimum spanning tree cost, which is polynomial time computable. So, even though we do not know this value, we have a polynomial time computable bound, because T minimum spanning tree we can compute in polynomial time. Okay. So, is that clear? Now, I have a 2 approximation algorithm for the TSP, metric TSP, because for general TSP we know that no polynomial ratio approximation algorithm is possible. Okay. So, notice that I am not really paying attention to the time here, I am caring only about the ratio, but each of these steps is a very small polynomial time. Finding a minimum spanning tree is m log n time, you are doubling every edge, and then Euler tour you can do in linear time, and then you are doing short circuiting. Okay. All these are very low polynomial time steps. Okay. So, now I want to actually improve the approximation ratio from 2 to 1.5, okay, because I said, right, that is the game here, you want to improve the approximation ratio. Okay, this came several years after the 2 approximation algorithm, but it is also nice and doable. So, 1.5 approx algorithm for metric TSP, 1.5 ratio. I did not formally define this approximation ratio, but you get the idea, right. So, the solution for a minimization problem, the solution produced by the algorithm by the optimum, that ratio is the approximation ratio over all instances, okay, the maximum ratio possible over all instances. So, this algorithm follows the same step more or less. So, why did I double every edge of t? To get what? Euler tour. I want to make every degree even, so that I have an Euler tour, right, and that is what was giving me this annoying cost of 2. I want to improve this ratio, right. Notice that to make every degree even, there are already some even degree nodes in the tree. So, why bother touching them? Only look at the odd degree nodes and do something with them. That is all we are going to do. So, step 1, find an MST. Step 2, okay, this is an algorithm you have not seen, but you just have to believe me. Find a minimum weight perfect matching on the odd degree nodes of T. So, let us call this M. Okay. So, I have my tree T, which looks like this. So, I need to worry about this node, because that is odd degree, this node, this node, this node. That is all the nodes I need to worry about. Recall that the graph is a complete graph, right, graph is a complete graph. So, I go to the induced subgraph of on these nodes, okay. They will have a perfect matching among them. Why? It is a complete graph, okay. Why should there be even number of vertices to start with? Because to have a perfect matching, you should have even number of vertices. Why should you have even number of vertices? The vertices I have ticked, I claim there will be even number of them, because number of odd degree nodes in any graph is even, right. First theorem you would have seen, number of odd degree nodes in any graph is even number. So, I have picked odd degree nodes in this minimum spanning tree, in this tree. So, that will be even number of them. Go to your graph, look at all the edges among them, right. In fact, in this tree itself I may have an edge, I do not have it here, but maybe let us say this is one more edge and this is odd degree, now this is also odd degree, right. So, this edge is also there. So, now I go to my graph and look at the induced subgraph on the odd degree nodes. It is a complete graph, because the original graph is a complete graph. So, there will be perfect matching, right. Among all the perfect matchings, I am saying find the minimum weight perfect matching. Okay. Now, this requires some work, but this can be done again using some flows and some more work. So, this is a black box, we have not done it, but it can be done in polynomial time, right. Given a weighted graph, you can find a minimum weight perfect matching if it exists. Given a weighted graph, complete graph, you can find a minimum weight perfect matching in polynomial time. Now, I am back to my game. So, what do I do? Find a, so add those edges now. Let us say my matching might pick this edge, maybe this edge and this edge. Add those edges. Okay. Now, what have I achieved? This tree plus the matching, every vertex has even degree, right, because the odd degree nodes have one extra edge now coming in. So, it is an Eulerian graph. Find an Euler too. Now, back to the same game. And the last step is the same, obtain a Hamiltonian circuit by short circuiting the Euler tour and output it. Okay, is the algorithm clear? Minimum spanning tree, pick the odd degree nodes of the minimum spanning tree and find a minimum weight perfect matching among them. And now, because now the graph has become Eulerian, because every degree is even now, find an Euler tour and short circuit to get a Hamiltonian cycle. We know how to do the short circuiting by not avoiding the repetitions, and we get this. Okay. So, that is the output. Now, I want to argue that, what do I need to argue? The solution produced is at most 1.5 times the cost of the optimum TSP2. So, the distance, total distance of the Hamiltonian cycle I have output is at most 1.5 times the total distance of optimum TSP. Okay. Distance. Okay. So, what is the cost of Hamiltonian cycle? Total distance is this cost of the minimum spanning tree plus what? Cost of the matching, the minimum weight perfect matching, because this is obtained from the Euler tour, right, because Euler tour cost, the Hamiltonian cycle cost is less than or equal to Euler tour cost because of triangle inequality, and this cost, Euler tour cost, is exactly cost of the minimum spanning tree plus the cost of the matching, minimum weight perfect matching on the odd degree nodes, and cost of the minimum spanning tree we already argued is cost of optimum TSP, right, because we take the TSP, remove an edge and you get a minimum spanning tree, and this is we have argued. So, now plus cost of the minimum weight perfect matching. Now, claim is the cost of the minimum weight perfect matching on the odd degree nodes you did is at most, what do I need to show? Half of the total distance of the optimum TSP. The cost of the matching, what is this? This is the minimum weight perfect matching on odd degree nodes of the minimum spanning tree. I want to show that this is less than or equal to half. I have been interchangeably using C and D, but you know what I am talking about, opt of TSP2. Okay, so what I will do is let us take the optimum TSP tour, right, this is take the optimum TSP tour which has all the vertices and look at the subtour which contains only the odd degree vertices of the spanning tree by doing some short circuiting. Okay. So, I care only about these vertices which are odd degree vertices in the spanning tree. Let us say it is these vertices. I remove every other vertex from this cycle. I do not just remove it, I will actually short circuit. So, what do I do? So, this all these guys are gone, I will directly draw this and look at this. Okay. So, short circuit to keep only vertices of O, the odd degree nodes of T, right? With me on that? Yeah. Yeah, there will be even number of them, sure. So, oh, you mean my example has odd number, okay, fine. Create another one, big deal, yeah. Now, so this cost of the short circuited tour containing only O is less than or equal to cost of the optimum TSP, right? Why? Triangle inequality again, right? One more line, we are done. But note that this cycle is actually a union of two matchings. Any cycle is a union of two matchings, right? So, what is this cost? Suppose this is my cycle on the vertices O. So, here is a matching and take the other edges, that is a matching, right. So, this cost is nothing but cost of some M1 plus cost of M2. Both of them are perfect matchings on the odd degree nodes. Are we done? Now, this must be greater than or equal to 2 times cost of M. M is the minimum weight perfect matching on O, right. So, each of M1 and M2 must be greater than or equal to C of M. Maybe one of them is equal to M, greater than or equal to. So, this is greater than or equal to 2 times C of M. So, from here we have cost of the matching is at most half of so this is actually equal to for some M1 and M2 which are perfect matchings on O, this each of this is greater than or equal to 2 times C of M. That is it. Isn't that what we wanted to show? Because I wanted to show that C of M is at most half of this. So, this algorithm, find a minimum spanning tree, find a minimum weight perfect matching on the odd degree nodes, Euler tour, short circuit to get a Hamiltonian cycle. It produces a Hamiltonian cycle whose cost is at most 1.5 times the optimum. Okay. And we are using this triangle inequality at many places, because whenever we are doing short circuiting, that the cost actually goes down or it never increases, relies on the fact that the distances satisfy triangle inequality. We saw two ratio 2 approximation algorithms for vertex cover, one using matching, one using linear programming. The linear programming one gives you a 2 approximation also for the weighted version of the vertex cover. And then we saw that the TSP problem, if the distances are completely arbitrary, then no polynomial ratio approximation algorithm is possible, but if the distances satisfy triangle inequality, then you can give you a 2 approximation or 1.5 approximation, and the tools of these algorithms are pretty much whatever you have seen, most of them in your last week lectures, right. Euler tour, minimum spanning tree, and I think this 1.5 is also the best known, or maybe recently there are some improvements for certain variants of traveling salesman problem, but I do not remember whether just for metric has been improved from 1.5 or not.